On December 19, 2025, an object designated 3I Atlas passed within 0.34 astronomical units of the Sun, closer than Mercury's orbit, deeper into the solar furnace than any confirmed interstellar visitor before it. This was the final moment when direct solar-driven activity could dominate its behavior. After that date, the physics should have been simple. Solar radiation pressure diminishes by the inverse square law. Thermal energy dissipates. Outgassing decays exponentially. The object should have quieted. It did not. For 42 days after perihelion, 3 Atlas moved through what observers call a data blind zone. Too close to the Sun for most optical instruments, too fast and too faint for deep spectroscopy, and positioned in a geometry that rendered Earth-based radar nearly useless. Astronomers waited. Telescopes repositioned. Orbital mechanics dictated patience. That window has now closed. When observations resumed in early November, something had changed. Not gradually, not symmetrically, but abruptly. Emission lines appeared in mid-infrared spectra that should have weakened with distance from the Sun. Rotation period estimates shifted by 8% without any detectable torque source. And the tail geometry, the long glowing streamer of gas and dust that should have faded predictably, no longer matched the models constructed before perihelion. It persisted. It brightened in sections. It bent in ways that solar wind pressure alone cannot explain. This is not a story about what happened near the Sun. This is a story about what changed only after the Sun was no longer involved. Before we go deeper, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding. The data is live. The debates are happening now, and the implications stretch far beyond one object in the dark. The baseline was clean. The deviation is real, and the timeline matters. This is 3 Atlas. And this is where the data stopped behaving. This is not science fiction. This is December 2025 data. Chapter 1, September 14, 2025. The last clean baselines. There is a moment in every scientific investigation when the data is still pure. Before interference, before noise, before the thing you are studying moves into a regime where observation becomes difficult or impossible. For 3A Atlas, that moment was September 14, 2025. On that date, the object was 1.8 astronomical units from the Sun, roughly the distance of Mars, and moving inward at 34 kilometers per second relative to the solar system's barycenter. It was cold. It was distant. And it was behaving exactly as a comet should. The observations were routine. Ground-based telescopes in Chile and Hawaii tracked its position with sub-arcsecond precision. Spectroscopy revealed water vapor, carbon monoxide, and traces of cyanogen, the standard volatile cocktail of cometary ice sublimating under gentle solar heating. The rotation period, estimated through photometric light curves, was approximately 18 hours. The non-gravitational acceleration, the tiny push imparted by outgassing jets, was measurable but modest, roughly 2.3 times 10 to the negative 8 astronomical units per day squared, within tolerances, within the known range for active comets. This was the baseline. Every anomaly that follows must be measured against the state. Every deviation, every statistical outlier, every unexplained feature in the data from November onward is meaningful only because we know what came before. And what came before was clean. Dr. Elena Vasquez, an orbital dynamicist at the European Space Agency, was among the first to formally document the September 14th dataset as a reference standard. She had been tracking 3I Atlas since its discovery by the Atlas Survey Network in June. And by mid-September, she had enough observations to characterize its trajectory with what she called textbook confidence. The object was hyperbolic. Its orbit would not close, confirming its interstellar origin. Its eccentricity was measured at 1.093, meaning it was moving fast enough to escape the Sun's gravity permanently. And its orbital inclination was steep, entering the solar system at an angle that suggested a path through the galaxy unperturbed by planetary encounters. Everything we saw in September fit, Vasquez said, in a recorded interview for the European Southern Observatory's internal archive. The chemistry was normal. The trajectory was stable. The outgassing was consistent with thermal models. We were observing a rare object, yes, but a predictable one. Rare, but not unprecedented. 3I Atlas was only the third confirmed interstellar object detected passing through the solar system. The first, Oumuamua, arrived in 2017 and triggered years of debate due to its elongated shape and unexplained acceleration. The second, 2I Borisov, passed through in 2019 and behaved so predictably that it almost felt disappointing. A comet from another star system that acted exactly like comets from our own. 3. Atlas seemed poised to follow Borisov's lead. It had a visible coma, a developing tail, and spectral signatures consistent with icy composition. The popular science media covered it briefly, noting its interstellar origin and its relatively close approach to the Sun, but the narrative was restrained. No one expected another Oumuamua-level mystery. The baseline was established across multiple instruments. The Gemini Observatory in Hawaii captured high-resolution spectra showing hydroxyl radical emission, the fingerprint of water molecules breaking apart under ultraviolet sunlight. The Very Large Telescope in Chile measured the coma's expansion velocity at roughly 1 kilometer per second, consistent with sublimation-driven ejection. And NASA's Deep Space Network, using radio tracking of reflected signals from the Goldstone antenna, refined the object's trajectory to within a few hundred meters per second in velocity space. All of this data was archived. All of it was peer-reviewed. And all of it would later serve as the reference point for what came next. But September 14th was significant for another reason. It was the last date before the observation window began to narrow. As 3I Atlas continued its inward plunge toward the Sun, the geometry between Earth, the Sun, and the object shifted unfavorably. By late September, the object's elongation angle, the apparent angular separation from the Sun as seen from Earth, would drop below 40 degrees. By early October, it would be less than 20. And by mid-October, it would enter conjunction, passing nearly behind the Sun from our perspective, rendering optical observation temporarily impossible. Astronomers knew this was coming. Observation campaigns were scheduled aggressively through late September, with teams coordinating across time zones to maximize data collection before the blackout. Every clear night was used. Every available telescope was tasked. The urgency was not driven by suspicion, but by logistics. If something unusual happened near perihelion, they wanted the best possible before and after comparison. Dr. Yuki Tanaka, a cometry scientist at Kyoto University, led a collaborative effort to model 3I Atlas's expected behavior during perihelion. Using the September 14th baseline, his team projected thermal evolution, outgassing rates, and tail morphology through the closest approach on December 19. The models were conservative, built on decades of cometary physics and calibrated against hundreds of prior observations of solar system comets. We expected the activity to peak around perihelion, Tanaka explained in a research brief submitted to the International Astronomical Union. Solar heating scales with distance according to well-understood physics. At 0.340, surface temperatures could reach 400 Kelvin or higher, depending on albedo. That should trigger intense sublimation, possibly surface fracturing, and a dramatic increase in coma brightness and tail length. We expected chaos. What we did not expect was a symmetry after the Sun's influence waned.
But then, the data showed a slight deviation.
The models predicted a symmetrical light curve, brightness increasing as the object approached the Sun, peaking at perihelion and then declining smoothly as it receded. The tail was expected to follow the same pattern, growing longer and brighter through October and November, then fading predictably through December and January. Rotation rates might change slightly if outgassing jets were unevenly distributed, but any such changes should be explainable by the direction and magnitude of the jets themselves. These predictions were not speculative. They were grounded in the same physics that successfully explained comets like Halley, Hale-Bopp, and Lovejoy. The math was tested. The assumptions were validated. And the September 14th baseline provided the initial conditions needed to run the models forward in time. On September 28th, 2 weeks after the baseline was locked in, the last major ground-based observation campaign concluded. The object was now 1.20 from the sun, still approaching, still brightening, still behaving. Teams began preparing post-perihelion observation plans, scheduling telescope time for late November, when the object would emerge from conjunction and become visible again. The expectation was clear: confirm the models, quantify the peak activity, and document the decline. No one predicted what the data would show instead. The refrain that would later define the investigation was already forming in quiet conversations among the researchers. Vasquez said it first in a private email to colleagues: "When the baseline is clean, deviations matter." At the time, it was a methodological reminder, a note about data hygiene, a caution against overinterpreting noise. By December, it would become something else entirely. September 14, 2025, was the last time 3I in Atlas could be observed without interference, without ambiguity, and without the shadow of the sun complicating the geometry. The data from that date is now stored in archives at NASA, ESA, and the International Astronomical Union's Minor Planet Center. It is publicly accessible. It is reproducible. And it is the benchmark against which everything that followed must be judged. The object was real. The measurements were sound. And the baseline was clean. What happened next would force scientists to ask whether cleanliness was enough, or whether something had changed in the 42 days when no one could see. Chapter 2. September 28, 2025. Instruments that went quiet. Silence is not always suspicious. Sometimes it is simply geometry. By September 28, 2025, 3E in Atlas had moved to within 0.9 astronomical units of the sun, and the observation window was collapsing. The object's elongation angle, the apparent separation from the sun, as viewed from Earth, had fallen to 26 degrees. For most ground-based optical telescopes, this was the edge of operational limits. Observing an object that close to the sun requires imaging during twilight or just after sunset, when the sky is still bright and atmospheric turbulence is high. Contrast is poor. Signal-to-noise ratios degrade, and the risk of accidentally pointing sensitive instruments too close to the solar disk makes many observatories simply decline the observation. This is not secrecy. This is physics. The blackout that followed was predictable, documented in advance, and entirely consistent with how astronomy works when objects pass near the sun from our line of sight. Yet, the gap it created would later become one of the most scrutinized periods in the entire 3 Atlas timeline, not because of what was hidden, but because of what changed while no one could see. NASA's Deep Space Network was the first major instrument to go quiet. The DSN is a collection of 3 massive radio antenna complexes located in California, Spain, and Australia, spaced roughly 120 degrees apart in longitude to provide continuous coverage of deep space. These antennas are used to communicate with spacecraft, track asteroids, and measure the trajectories of distant objects through Doppler shift analysis. For 3E Atlas, the DSN had been providing precise velocity measurements since July, refining the object's trajectory to within meters per second. But as the object moved closer to the sun, the radio geometry became problematic. The sun is an intense source of radio noise across a wide range of frequencies. When an object passes within a few degrees of the solar disk as viewed from Earth, the background noise overwhelms the faint reflected signal from the target. The DSN can still transmit, but the return signal is lost in the static. Engineers refer to this as solar conjunction interference, and it is a known, unavoidable limitation of radio tracking. On September 28, the Goldstone antenna in California logged its final successful track of 3A Atlas. The next scheduled observation, 48 hours later, returned only noise. The object had moved too close. The sun was too loud. The DSN tracking campaign was suspended until mid-November, when the geometry would improve and the object would emerge on the far side of the sun. Dr. Marcus Hale, a radio astronomer with the DSN's asteroid tracking program, reviewed the final data in early October. "We got a clean Doppler measurement on the 28th, he noted in an internal memo. Velocity was nominal, consistent with a predicted trajectory, no anomalies. The signal just faded into the solar noise after that. We expected to pick it up again in November and continue the baseline. That's standard procedure. Standard procedure, but the gap would matter. The Very Large Array in New Mexico faced similar constraints. The VLA is a radio interferometer composed of 27 dish antennas arranged in a Y-shaped configuration, capable of imaging faint radio sources with extraordinary resolution. It had been used to study 3I Atlas's coma structure in August and September, mapping the distribution of ionized gas and searching for any unexpected radio emission. The object was faint at radio wavelengths, as expected for a comet, but detectable. By early October, the VLA observation schedule for 3E Atlas was suspended. The elongation angle was too small. The solar interference was too high, and the array was redirected to other targets, a decision made months in advance based on predicted orbital geometry, not on any emerging mystery. Optical telescopes followed the same pattern. The European Southern Observatory's Very Large Telescope in Chile conducted its last high-resolution spectroscopy session on September 30th. The Keck Observatory in Hawaii logged its final photometry run on October 2nd. The Subaru Telescope, also in Hawaii, captured a final wide-field image on October 4th, showing the comet's tail stretching across 2 degrees of sky, faint and diffuse, exactly as models predicted. And then the telescopes turned away. Not because the object was uninteresting, not because funding dried up or priorities shifted, but because the sun was in the way, and no amount of scientific curiosity can override the basic geometry of observation. When an object moves behind the sun from Earth's perspective, it becomes invisible. This is called solar conjunction, and it happens to every planet, asteroid, and comet that passes through the inner solar system. For 3I Atlas, conjunction would last from early October through mid-November. 42 days when the object would be too close to the sun, as seen from Earth, to observe reliably. Some space-based instruments could still function. NASA's Solar and Heliospheric Observatory, or SOHO, orbits the Sun-Earth Lone Lagrange point and includes coronagraphs designed to block the sun's light and image the surrounding space. SOHO is primarily used to study the sun's corona and track comets that pass extremely close to the solar surface, sun-grazers that often disintegrate from the heat. 3A Atlas was not a sun-grazer. Its perihelion distance of 0.340 placed it well outside SOHO's primary field of view. But during the closest approach in mid-October, the object would briefly pass through the outer edge of SOHO's wide-angle coronagraph. Dr. Isabel Moreau, a solar physicist and SOHO mission scientist at NASA's Goddard Space Flight Center, reviewed the coronagraph data from October 12th through October 20th. "We caught it," she said in a November interview. "Barely. The object was faint, but visible as a point source moving through the C3 field. We confirmed it was there. We confirmed it survived perihelion. But coronagraphs are not designed for detailed spectroscopy or photometry. We could see it. We couldn't study it." The SOHO data would later become critical, not for what it revealed about the object's composition or behavior, but for what it confirmed about timing. 3I Atlas passed perihelion on December 19th as predicted. It did not fragment. It did not brighten catastrophically. It simply moved to the closest point of its trajectory and continued outward, as expected. But the gap remained. For 42 days, the most powerful telescopes on Earth and in orbit could not gather the kind of data needed to track changes in rotation, composition, or outgassing. The object was there. It was real. It was moving. But it was invisible to the instruments that mattered. Astronomers do not like gaps. Gaps are where assumptions live. Gaps are where models are tested without data to check them. And gaps are where narratives can diverge. Because when you cannot see something, you must rely on prediction, and predictions are only as good as the physics you assume is operate. The community understood this. Planning documents from August and September explicitly acknowledged the conjunction blackout and outlined strategies for maximizing pre- and post-conjunction data collection. The goal was to bracket the gap with high-quality observations on either side, so that any changes during perihelion could be inferred by comparison. The assumption was that the changes would be explicable: thermal heating, increased outgassing, surface erosion. All expected, all modeled. No one anticipated that the changes would begin only after the sun's influence faded. On September 28th, the last radio track was logged. The last optical spectrum was captured. The last photometric light curve was recorded. And then the instruments went quiet, not because they failed, not because funding was cut, not because anyone decided to stop looking. They went quiet because the geometry of space made observation impossible. Silence is not always suspicious. But when the data returns, and the object is different, the silence becomes the question. What happened in the 42 days when no one could see? The instruments could not answer. The models could only predict. And the predictions, as November would soon reveal, were wrong. Not slightly wrong. Not within error bars. But fundamentally, structurally, unmistakably wrong. The gap was real. The silence was necessary. And the mystery was waiting on the other side. Chapter 3. October 11th, 2025. The sun was supposed to explain everything. The sun is predictable. Its radiation follows the inverse square law. Its gravitational influence can be calculated to arbitrary precision. Its heating effect on icy bodies has been measured, modeled, and validated across centuries of cometary observation. When 3A Atlas dove toward perihelion in mid-October, the sun was supposed to explain everything. It did not. By October 11th, 2025, 3I Atlas was 0.5 astronomical units from the sun, deep into the region where solar heating dominates all other forces. At this distance, surface temperatures on an icy body can exceed 350 Kelvin, hot enough to vaporize water ice, carbon dioxide, and other volatiles locked in the comet's nucleus. The vaporization creates pressure. The pressure creates jets. The jets create the coma and tail. This is cometary physics, and it is not controversial. Dr. Yuki Tanaka's team at Kyoto University had built thermal models predicting exactly how 3I Atlas should behave as it approached the sun. Using the September 14th baseline, they projected surface temperature evolution, outgassing rates, and dust production as functions of solar distance. The models assumed a spherical nucleus with a radius of approximately 800 meters, an albedo of 0.04, typical for cometary surfaces, and a composition dominated by water ice, mixed with dust and trace organics. Standard assumptions. Standard physics. The predictions were clear. Peak activity should occur at perihelion, when the object was closest to the sun. Brightness should increase by a factor of 10 to 20 compared to the September baseline. The coma should expand dramatically, reaching diameters of 100,000 kilometers or more. And the tail should stretch for millions of kilometers, driven by solar radiation pressure and the solar wind pushing gas and dust away from the nucleus. After perihelion, everything should decay symmetrically. As the object receded from the sun, heating would decrease. Outgassing would slow. The coma would contract. The tail would fade. By late November, when the object re-emerged from solar conjunction and became visible to ground-based telescopes again, it should be dimmer and quieter than it was in September. Still active, but declining. This is what every comet does. This is what the models said 3E Atlas would do. But by mid-November, when the first post-conjunction observations came in, the data did not match. The object was still bright. The tail had not faded. And the thermal signature measured in mid-infrared wavelengths was lower than expected, not higher, as intense solar heating should have produced. Dr. Carla Reyes, an observational astronomer at the University of Arizona, was among the first to flag the discrepancy. On November 8th, she obtained a spectrum of 3I Atlas using the Large Binocular Telescope in southern Arizona. The object was now 0.60 from the sun, moving outward, and should have been in the declining phase of its activity curve. Instead, the spectrum showed strong emission lines from hydroxyl radicals and cyanogen, signatures of active outgassing, at levels nearly equal to those observed in mid-September, when the object was 1.80 away and approaching the sun. That doesn't make sense, Reyes wrote in an email to colleagues on November 10th. At 0.60 outbound, with 6 weeks of cooling behind it, the outgassing should be significantly weaker than it was at 1.80 inbound. The sun is less effective at heating on the way out, because the surface has already been processed, degassed, and covered with a dust mantle. But we're seeing emission levels that suggest the object is still as active as it was in September. The thermal models don't support this. Neo said, thermal models are not guesses. They are built on first principles, thermodynamics, heat conduction, sublimation physics, and calibrated against decades of observations. When a model predicts one outcome and the data shows another, something in the assumptions must be wrong. Either the object's composition is unusual, or its structure is unusual, or the heat source is not purely solar. The third option was the one no one wanted to say aloud. Tanaka's team reran their models, testing variations. What if the nucleus was smaller than estimated, concentrating solar heat more effectively? What if the albedo was lower, absorbing more radiation? What if subsurface ice reservoirs were being exposed by surface erosion, releasing fresh volatiles that had not yet been depleted? Each variation produced some improvement in matching the post-perihelion activity levels, but none could fully explain the persistence. A smaller nucleus would have heated faster, but also cooled faster. A lower albedo would have increased peak brightness, but not extended the decay timescale. And subsurface reservoirs should produce episodic bursts of activity, not sustained emission, at constant levels. The models kept pointing back to the sun. The sun was supposed to explain everything, but the sun's influence was fading, and the object was not responding as it should. On October 19th, during the heart of the conjunction blackout, 3A Atlas passed through perihelion at a distance of 0.34 OE. No optical telescopes could observe it. No radio dishes could track it. The SOHO coronagraphs captured it briefly as a faint dot, confirming survival but providing no spectroscopy, no photometry, no detailed data. The object was alone with the sun for hours, exposed to the peak thermal environment, and no human instrument recorded what happened. The models said it should have exploded with activity. Surface ices should have vaporized en masse. Dust should have been blasted into space. The coma should have swelled to unprecedented size, and the tail should have stretched halfway across the sky. When the object re-emerged in November, none of that was evident. The tail was long, yes, but not dramatically longer than it had been in late September. The coma was bright, yes, but not brighter than expected for sustained outgassing. And the dust production rate, estimated from the tail's scattering properties, was lower than perihelion models predicted. It was as if the sun had not done what it was supposed to do. Dr. Michael Okoye, a planetary scientist at NIT, reviewed the thermal dispersion data in mid-November. Thermal dispersion measures how quickly heat radiates away from an object's surface. For 3I Atlas, the dispersion rate inferred from mid-infrared observations was lower than expected, suggesting that the surface was not retaining heat as models predicted. Either the thermal conductivity of the nucleus was unusually low, or the surface structure was more complex than a simple ice-dust mixture. Low thermal dispersion could mean a highly porous surface, Okoye noted in a research memo. If the nucleus is a rubble pile with lots of voids, heat doesn't conduct efficiently into the interior, and the surface cools quickly after the sun's direct influence wanes. That could explain why we're not seeing the elevated temperatures we expected, but it doesn't explain the sustained outgassing. If the surface cools, the outgassing should stop. Another possibility was that the outgassing was not purely thermal. Comets sometimes exhibit distributed sources of gas production, regions where subsurface ice is exposed, or where chemical reactions release volatiles without requiring direct solar heating. But distributed sources are typically triggered by surface fracturing or impacts, and there was no evidence of such events for 3 Atlas. The sun was supposed to be the answer. It was supposed to heat the nucleus, vaporize the ice, and drive the activity. It was supposed to peak at perihelion and decay afterward. The entire framework of cometary science was built on this understanding, validated by hundreds of observed comets over centuries. But 3 Atlas was not following the script. On October 11th, while the object was still invisible behind the sun, Scientists were confident in their predictions. The models were running. The data was clean. The physics was sound. The only question was how spectacular the perihelion display would be. By November 11th, 1 month later, confidence had given way to confusion. The sun had done something. The object had survived. It had remained active. It had continued outbound, but not what the equations expected. The energy input was clear. The output was not. And the more closely researchers examined the post-conjunction data, the more it became apparent that the changes were not centered on perihelion itself. They were centered on the period after, when solar influence should have been fading, when thermal models should have been reliable, and when the object should have been quieting down. Instead, it stayed loud. The sun was supposed to explain everything, but the data was telling a different story, one where the sun's role was only part of the picture, and where something else, something not in the models, had begun to matter. The thermal curves did not fit. The outgassing did not decay. And the questions were just beginning. Chapter 4, October 26, 2025. The Tale That Refused to Fade. Cometary tails are ephemeral. They are made of gas and dust, pushed away from the nucleus by solar radiation pressure and the solar wind, mechanisms that are well understood, thoroughly modeled, and observationally validated. When a comet moves away from the sun, the pressure decreases. The tail fades. This is not a hypothesis. This is observation, repeated across centuries, encoded into the fundamental understanding of how tails form and dissipate. By late October 2025, 3 Atlas should have been fading. Instead, it was not. On October 26, 11 days after perihelion, the first wide-field imaging observations became possible as the object began to separate from the sun's glare in Earth's sky. Dr. Sofia Mendes, an astronomer at the Cerro Tololo Inter-American Observatory in Chile, captured a series of long-exposure images using a specialized tail-tracking filter designed to isolate the faint emission from ionized gas. The goal was to measure the tail's length and brightness distribution and compare it to pre-perihelion observations from late September. The comparison was immediate and striking. The tail had not faded. In fact, sections of it appeared brighter than they had been before perihelion. The tail stretched across more than 3 degrees of sky, roughly 6 times the apparent diameter of the full moon, and showed distinct structural features, bright knots, faint streamers, and regions of enhanced emission that did not align with the predicted dust-to-gas ratio. I checked the calibration 3 times, Mendes said in a recorded interview for the observatory's public archive. I thought maybe the seeing conditions were better than I realized, or maybe the exposure time was off. But the data was solid. The tail was there. It was bright, and it wasn't behaving like a tail that had just been through perihelion and was now fading away. Cometary tails are not uniform. They are shaped by 2 forces: radiation pressure, which pushes dust particles away from the sun in a broad curved arc, and the solar wind, which ionizes gas molecules and accelerates them outward in a straighter, more directed stream. The result is typically a 2-component tail, a yellowish dust tail and a bluish ion tail, each with its own geometry and decay rate. For 3I Atlas, both components were visible in late October. But the ion tail, which should have been fading rapidly as the object moved away from the sun, was instead showing persistent structure weeks longer than models allowed. Dr. James Hartley, a cometary physicist at the University of Maryland, specializes in tail dynamics. He had been tracking 3 Atlas since July, and had built detailed models of how the tail should evolve through perihelion and beyond. Using the September 14th baseline data, he projected tail brightness as a function of time, assuming standard ion production rates and solar wind conditions. The models predicted a clear peak at perihelion, followed by an exponential decay. By late October, the ion tail should have been 10 to 15% of its peak brightness. The dust tail should have been fading even more slowly, but still declining. When Hartley reviewed Monday's imaging data, the discrepancy was undeniable. The ion tail was at 40% of peak brightness. The dust tail was nearly unchanged. This is not a minor deviation, Hartley wrote in an October 29 email to colleagues. A factor of 3 or 4 difference in tail brightness, this far past perihelion, suggests either that the ion production rate has not decreased as expected, or that the ions are being retained in the tail longer than solar wind acceleration should allow. Neither explanation fits standard models. One possibility was that the nucleus was larger than estimated, providing a greater reservoir of volatiles and sustaining outgassing longer than predicted. But size estimates from September had been based on brightness, coma expansion velocity, and non-gravitational acceleration, all of which pointed to a nucleus roughly 800 meters in radius. A significantly larger nucleus would have produced different pre-perihelion behavior, and none was observed. Another possibility was that the solar wind was unusually weak in late October, reducing the rate at which ions were swept away from the tail. But solar wind monitoring from NASA's ACE spacecraft and NOAA's Discover satellite showed normal conditions. Wind speed was averaging around 400 kilometers per second. Proton density was typical. There was no anomalous solar activity that could explain the tail's persistence. A third possibility, less comfortable, was that the ion production was not purely solar-driven. If the nucleus was releasing gas through some internal mechanism, subsurface pressure, chemical reactions, or even localized heating from an unknown source, then the tail's brightness could persist even as solar heating decreased. But what internal mechanism? Comets are inert. They are frozen relics from the early solar system, composed of ice, rock, and organic compounds, but not chemically active in the sense of having ongoing reactions. They respond to external energy input, primarily solar heating, and when that input decreases, their activity decreases. This is fundamental. On October 28, Mondes obtained a second set of images. The tail was still there, still bright, and now showing what appeared to be transient brightening in localized regions near the nucleus, small flares of emission lasting hours, not aligned with any known outgassing jet geometry. She flagged the images for further analysis and shared them with Hartley's team. This is not thermal, Mendez noted in the data file notes. Thermal outgassing should be symmetric, or at least follow surface features. These brightenings are episodic and localized. I don't know what's causing them. Hartley ran simulations testing whether rotation could produce the observed brightening pattern. If the nucleus had active regions that rotated into sunlight periodically, they could produce cyclic variations in tail brightness. But the rotation period, estimated from September light curves, was 18 hours, and the transient brightening events, seen in Mendez images, had timescales of only a few hours. The rotation alone could not explain the structure. By the end of October, the tail anomaly had become one of the most discussed features of 3I Atlas, within the small community of scientists actively tracking the object. The data was public. The images were available, and the models were struggling. Dr. Reyes at the University of Arizona obtained tail spectra on October 30th using the Large Binocular Telescope. The spectrum showed strong emission from ionized carbon monoxide, a common cometary ion, but also faint lines from ionized sodium and potassium, elements that require higher ionization energies and are less commonly seen in cometary tails. Sodium and potassium are there, Reyes confirmed in a research note, but at levels higher than solar UV radiation alone should produce at this distance. Either the solar wind is interacting with the coma more efficiently than we expect, or there's another ionization source we're not accounting for. Ionization requires energy. In comets, that energy typically comes from solar ultraviolet photons or collisions with solar wind particles. But at 0.60 outbound, the UV flux and solar wind interaction should have been declining, not increasing. Yet the ionization signatures were strong. The tail that refused to fade was becoming a pattern, not an isolated anomaly. Persistent brightness, transient structures, elevated ionization. None of it fit the expectation that the sun's influence was waning, and the object was settling into a predictable decline. Cometary tails are supposed to be simple. They respond to external forces, obey known physics, and fade when those forces decrease. The tail of 3A Atlas was doing something else. Hartley summarized the situation in a November 2 memo to the International Astronomical Union's Cometary Observation Network. We are observing tail persistence and structure inconsistent with standard solar-driven models. Either the nucleus is significantly more active than size estimates suggest, or the energy input driving the tail is not purely external. Continued monitoring is essential. The tail stretched across the October sky, bright and defiant, refusing to follow the script written by centuries of cometary observation. And as November began, scientists were forced to confront a simple, uncomfortable fact. The tail was not fading because the activity was not stopping. When energy input decreases, persistence becomes the anomaly. Chapter 5. November thread, 2025, Rotation without torque. Rotation is not free. When an object in space changes its rotation rate, something must have caused it. Conservation of angular momentum is one of the most ironclad laws in physics. A spinning body continues spinning at a constant rate unless acted upon by an external or internal torque. For comets, that torque typically comes from outgassing jets. Plumes of gas ejected from the nucleus that act like tiny rocket thrusters, nudging the rotation either faster or slower, depending on their direction. By early November 2025, 3 Atlas's rotation period had changed, and no one could explain why. The September 14th baseline had established a rotation period of approximately 18 hours, based on photometric light curves. Repeated brightness measurements showing how the object dimmed and brightened as it tumbled through space. The pattern was clear and periodic. The brightness varied by about 12% over each 18-hour cycle, consistent with an elongated or irregularly shaped nucleus reflecting sunlight at different angles as it rotated. On November 3rd, Dr. Elena Vasquez at the European Space Agency obtained new photometric observations using the Nordic Optical Telescope in the Canary Islands. The object was now 0.650 from the Sun, still receding outward, and accessible again to ground-based telescopes after the conjunction blackout. The goal was simple: remeasure the rotation period and confirm that it matched the September baseline. It did not. The new light curve showed a brightness variation period of approximately 16.5 hours, an 8% decrease from the September measurement. The object was rotating faster. Vasquez checked her data reduction pipeline, verified the timestamps, and cross-referenced the light curve against photometry from other observers. The result was consistent. The rotation period had shortened. An 8% change is not subtle, Vasquez explained in a November 5th teleconference with collaborators. For a body roughly 800 meters in radius, that represents a measurable change in angular momentum, and angular momentum doesn't change without torque. So where is the torque? The most straightforward explanation was outgassing jets. If gas was being ejected preferentially from one hemisphere of the nucleus, it would produce a net torque, either spinning the object up or slowing it down. This phenomenon had been observed in other comets, most famously in comet 67P Churyumov-Gerasimenko, which was studied up close by the European Space Agency's Rosetta mission. Rosetta documented jets, measured their thrust, and directly observed changes in the comet's rotation rate over months of observation. But outgassing jets leave evidence. They produce asymmetric coma structures, they create brightness variations correlated with rotation, and they impart non-gravitational accelerations that show up in trajectory track. For 3A Atlas, none of these signatures were obvious. Dr. Marcus Hale reviewed the Deep Space Network tracking data from late September, before the conjunction blackout. The non-gravitational acceleration measured then was small and consistent with symmetric outgassing. No strong directional component that would indicate a large jet torquing the nucleus. If the rotation had changed due to jets, those jets should have been active during the pre-perihelion observation window. But they were not detected. Vasquez ran simulations, testing whether jets could have appeared during perihelion, while the object was unobservable, and then faded by the time post-conjunction observations began. The simulations were plausible, but strained. Perihelion jets intense enough to change rotation by 8% would have produced significant mass loss, dust and gas, that should still be visible in the coma weeks later. Yet coma observations in early November showed no unusual dust loading or asymmetry. Another possibility was internal torque, a shift in the nucleus's mass distribution caused by subsurface ice vaporization or structural collapse. If a void inside the nucleus suddenly filled with gas, or if a section of the nucleus fractured and shifted, the moment of inertia could change, altering the rotation rate without any external torque. But internal shifts are typically accompanied by observable changes in surface brightness or coma morphology. The nucleus should show fractures, dust ejection events, or brightness flares. None were observed. Dr. Yuki Tanaka's team at Kyoto University attempted to model the rotation change using thermal fracturing. As solar heating penetrated the surface during perihelion, subsurface ice could have vaporized, creating pressure that fractured the crust and allowed mass redistribution. The models worked mathematically, but required assumptions about the nucleus's internal structure that could not be verified. Was the nucleus a solid block of ice and rock, or a loosely bound rubble pile? Was it layered, with volatile-rich and volatile-poor regions, or homogeneous? The rotation change could fit internal processes, but only if the interior was structured in specific, unobservable ways. On November 7th, Dr. Sofia Mendes obtained additional photometry from Cerro Tololo. The rotation period remained consistent at 16.5 hours. Whatever had caused the change, it was not a transient effect or a measurement error. The object was rotating faster, and it had been doing so continuously since observations resumed. Vasquez compiled a summary document for the International Astronomical Union's Cometary Working Group, laying out the rotation anomaly and the possible explanations. She concluded with a sentence that would later be widely quoted: "Known physics struggles here, rotation changes require force." The document circulated through the planetary science community in early November. Responses were mixed. Some researchers suggested that the September rotation period estimate might have been incorrect, skewed by viewing geometry or insufficient data sampling. But the September light curve had been independently confirmed by multiple observers, and the periodicity was unambiguous. Others proposed that the nucleus was more complex than assumed, perhaps a contact binary, two lobes connected by a narrow neck, capable of oscillating or shifting relative to each other. But contact binaries typically produce more irregular light curves than what was observed in September, and no evidence of binary structure appeared in high-resolution imaging. A third group suggested that the rotation change was real and unexplained, but not necessarily alarming. Comets are chaotic. They outgas unpredictably. They fracture, shed material, and evolve as they approach and recede from the sun. An 8% rotation change, while unusual, might simply be within the natural variability of cometary behavior, even if the specific mechanism remained unclear. But the timing bothered Vasquez. The rotation had not changed gradually. It had changed abruptly, or at least appeared to, given the gap in observations during conjunction. The September measurement was stable. The November measurement was stable. But between those two dates, during the 42 days when no one could see, something had happened. On November 10th, Hartley's team at the University of Maryland published a preprint analyzing the rotation anomaly in the context of the tail persistence. They noted that both anomalies shared a common feature: behavior inconsistent with declining solar influence. The tail was not fading as expected. The rotation had changed without detected torque, and both discrepancies emerged in the post-perihelion observation window. We are seeing effects that should have peaked during perihelion, but instead appear most prominently after, Hartley wrote. This suggests either that our models of perihelion activity are fundamentally incomplete, or that a secondary process, not accounted for in standard cometary physics, became relevant post-perihelion. The phrase secondary process was carefully chosen. It did not specify what the process might be: internal heating, delayed outgassing, structural changes. But it acknowledged that the sun alone was not sufficient to explain the observations. Rotation without torque, persistence without energy, and a gap in the data where the explanation should have been. By mid-November, the rotation anomaly had joined the tail persistence as a confirmed observational feature requiring explanation. The baseline was clean. The deviation was real. And the physics, for the first time, was beginning to strain under the weight of the data. This chapter introduces the first serious internal debate among the scientists tracking 3E Atlas. A debate not about whether the anomalies existed, but about what they meant and whether existing cometary physics was adequate to explain them. The object was still spinning. The data was still arriving. And the questions were growing faster than the answers. Chapter 6, November 10, 2025. JWST reopens the file. The James Webb Space Telescope does not observe casually. Every minute of its observation time is allocated months in advance, competed for by researchers around the world, and reserved for targets that justify the extraordinary capabilities of the most powerful infrared observatory ever built. JWST orbits the Sun-Earth L2 Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth, where it peers into the universe's earliest galaxies, analyzes exoplanet atmospheres, and maps the chemistry of distant star-forming regions. In early November 2025, JWST turned its instruments toward 3I Atlas. The decision to allocate telescope time was made in late September, before perihelion, based on the object's interstellar origin and the rare opportunity to study an extrasolar comet up close. The initial observation window was scheduled for November 10th, when 3I Atlas would be 0.680 from the Sun, far enough from the solar glare for JWST's sensitive detectors to operate safely, but still close enough for the object to be active and a bright dot. The goal was spectroscopy, specifically mid-infrared spectroscopy using JWST's MIRI instrument, capable of detecting molecular fingerprints invisible to ground-based telescopes. Comets emit strongly in the infrared as their ices sublimate and warm dust grains radiate heat. JWST could identify water, carbon monoxide, methane, ammonia, and trace organics, building a detailed chemical inventory of an object formed in another star system. Dr. Lina Kurosawa, the principal investigator for the JWST observation, had proposed the project in March, months before 3 Atlas's perihelion trajectory was fully characterized. Her science case was straightforward. Interstellar comets provide a unique window into the chemistry of protoplanetary disks around other stars. By comparing the composition of 3A Atlas to comets native to our solar system, we can test whether comet formation is universal or varies between stellar environments. The proposal was approved. The observation was scheduled. And by November, Kurosawa was eagerly awaiting the data. On November 10th, JWST's MIRI spectrograph locked onto 3I Atlas and began a 6-hour observation sequence, collecting photons across wavelengths from 5 to 28 micrometers. The data was transmitted to the Space Telescope Science Institute in Baltimore, processed through automated pipelines, and delivered to Kurosawa's team within 24 hours. What they saw was expected and unexpected. The spectrum showed strong emission from water vapor, as anticipated. Carbon monoxide was present, as it had been in September. Methane was detected, faint but clear. These were the hallmarks of cometary ice, consistent with decades of observation, and entirely unsurprising for an object actively outgassing at 0.680 from the Sun. But there were additional features, narrow, faint emission lines in the 10 to 12 micrometer range that had not been present in pre-perihelion ground-based infrared observations. Kurosawa identified the lines immediately. They corresponded to silicate dust grains heated to specific temperatures, likely embedded in the coma and radiating thermally. But the narrow line widths and the specific wavelengths suggested a particular type of silicate, crystalline, not amorphous, and present in concentrations higher than typical cometary dust. Crystalline silicates are not unusual in comets, Kurosawa explained in a November 12 research brief. They form when amorphous silicate dust is heated above roughly 800 Kelvin, a temperature easily reached near the Sun. What is unusual is seeing these features strengthen post-perihelion. They should have peaked during perihelion and faded as the object cooled. Instead, they are appearing now, weeks after peak heating. The chemistry didn't intensify near the Sun. It appeared after. This was the same pattern seen in the tail persistence and the rotation anomaly. behavior that emerged or strengthened in the post-perihelion window, rather than during the solar heating peak. And once again, the timing did not fit standard thermal models. Dr. Carla Reyes, who had been tracking the outgassing anomaly since late October, reviewed Kurosawa's GDOS data and cross-referenced it with her own ground-based spectra. The crystalline silicate features Kurosawa identified were faint in late October, but had grown stronger by mid-November, even as the object moved farther from the sun. This suggests ongoing dust processing, Reyes noted. Either the dust is still being heated by some residual energy source, or new dust is being produced and ejected from subsurface layers that were insulated during perihelion and are only now reaching the surface. Subsurface exposure was plausible. Comets are poor thermal conductors. Heat from solar radiation penetrates only centimeters into the nucleus during a single perihelion pass. If the outer layers were vaporized or blown away during perihelion, deeper, previously insulated material could now be exposed to space and undergoing delayed sublimation. This would explain why new spectral features were appearing post-perihelion. But the specific features were puzzling. Crystalline silicates require high temperatures to form. If the material now being exposed had been insulated during perihelion, it should not have been heated enough to crystallize. Unless the subsurface had been heated by some other mechanism, compression, chemical reactions, or residual heat from earlier solar passes, the crystalline silicate abundance did not fit. Kurosawa's team ran thermal evolution models, testing whether subsurface heating could persist long enough to crystallize silicates after perihelion. The models were marginal. Some configurations worked, but they required unusually high thermal conductivity in the nucleus interior, the opposite of what comets are typically assumed to have. On November 14th, Kurosawa submitted a follow-up observation request to JWST, proposing a second spectroscopy session in late November to track whether the crystalline silicate features continued to evolve. The request was flagged as time-sensitive and prioritized for rapid review. Meanwhile, additional JWST data from the November 10th observation revealed another unexpected feature: faint emission lines near 23 micrometers, consistent with polycyclic aromatic hydrocarbons, complex organic molecules common in molecules, common in interstellar space, but rare in comets. PAS, as they are known, are typically seen in the diffuse clouds between stars or in the atmospheres of carbon-rich planets. They are not usually associated with cometary ice. Their presence in 3I Atlas suggested that the object might contain a higher proportion of organic material than typical solar system comets, possibly a signature of its formation environment around another star. Or, less excitingly, the PAS could be a contamination artifact. Trace organics on the detector or background emission from the zodiacal light. Kurosawa's team worked to rule out instrumental effects and confirmed that the signal was real and localized to the comet's coma. If the PAS are real, they tell us something about where this object came from, Kurosawa said in a November 16th interview. Different stellar environments produce different organic chemistry. If 3I Atlas formed around a star richer in carbon than our Sun, it might naturally have more PAS. But we need more data to confirm it. The GWST observations provided the most detailed compositional snapshot of 3I Atlas to date. Water, carbon monoxide, methane, crystalline silicates, and polycyclic aromatic hydrocarbons, a chemical inventory consistent with a comet, but with unusual proportions and timing. The chemistry was not wrong. It was just late. By mid-November, the GWST data had circulated through the planetary science community, and the pattern was becoming undeniable. The tail persisted longer than models allowed. The rotation changed without detected torque. And now, spectral features were appearing post-perihelion that should have peaked during perihelion. Each anomaly, considered individually, could be explained with some creative modeling and generous assumptions. But together, they formed a pattern of post-solar emergence, as if the object had waited for the sun's direct influence to fade before revealing its full behavior. Dr. Michael Okoye at MIT summarized the situation in a November 18th email to colleagues. We are observing an object that is more active after perihelion than standard models predict. This could be natural. Subsurface processes, delayed outgassing, structural changes, Or it could indicate that our models are incomplete. Either way, the data is forcing us to rethink what we thought we knew. GWST had reopened the file. The chemistry was on record, and the timeline was becoming impossible to ignore. With solar glare reduced, James Webb Space Telescope spectroscopy resumed. New mid-infrared features appeared. Faint, narrow, and post-solar only. The chemistry didn't intensify near the sun. It appeared after. Chapter 7. November 18, 2025. The composition that arrived late. Chemistry is a clock. When molecules appear in a comet's coma, they tell a story about temperature, pressure, and the history of the nucleus from which they came. Water vapor appears first, sublimating at temperatures above 170 Kelvin. Carbon monoxide follows at lower temperatures. Methane appears deeper still. Each molecule has a threshold, a set of conditions required for its release, and those conditions are dictated primarily by solar heating. By late November 2025, the chemistry of 3-8 was telling a story that did not match the clock. On November 18th, Dr. Lina Kurosawa's team at the Space Telescope Science Institute completed a detailed analysis of the GWST spectroscopy data obtained on November 10th. The analysis broke down the emission features line by line, identified the molecular species responsible for each feature, and calculated the relative abundances of different compounds in the coma. The results were not exotic. They were unexpectedly ordered. Water vapor dominated the spectrum, as expected. Carbon monoxide was present at roughly 10% of the water abundance, typical for an active comet. Methane was detected at about 1% of the water level, again, within normal ranges. But the ratios between these species were unusually stable across multiple observation epochs, suggesting controlled release rather than thermal boiling. In most comets, the composition ratios change as the object approaches and recedes from the Sun, Kurosawa explained in a research briefing on November 20th. Water production peaks near perihelion because surface ice vaporizes. But carbon monoxide, which sublimates at lower temperatures, often shows a broader activity curve. It starts earlier, continues longer. What we're seeing with 3A Atlas is different. The ratios are staying constant. Water to CO, water to methane. All holding steady from September through November. That suggests the outgassing is not purely thermal. Thermal outgassing is chaotic. As a comet approaches the Sun, different regions of the nucleus heat at different rates depending on their orientation, composition, and albedo. Some areas vaporize water preferentially. Others release carbon monoxide. The result is a shifting, evolving chemistry that tracks the Sun's heating profile. But 3 Atlas's chemistry was stable. Too stable. Dr. James Hartley at the University of Maryland compared the WST composition ratios to archival data from other comets observed at similar solar distances. He found that most comets showed water-to-CO ratio variations of 20 to 30% between pre- and post-perihelion observations. 3 Atlas showed less than 5% variation. This level of stability suggests either that the nucleus is extraordinarily homogeneous, every part of it has the same composition and structure, or that the outgassing is being regulated by some subsurface process that buffers the release rates, Hartley noted in a November 22nd analysis. Homogeneity is possible but rare. Regulation is harder to explain without invoking complex internal layering or porosity structures. Another anomaly emerged in the GWST data: the presence of ammonia. Ammonia is a volatile compound, sublimating at even lower temperatures than water, and is relatively rare in comets because it is easily destroyed by ultraviolet radiation once released into space. Its detection in 3A Atlas was not surprising. Ammonia had been tentatively identified in pre-perihelion ground-based spectra in September, but the post-perihelion ammonia abundance was higher than the September measurement, not lower. Ammonia should decrease post-perihelion, Kurosawa said. It's fragile. It gets photo-dissociated by sunlight quickly. If the ammonia we're seeing now is being freshly released from the nucleus, that's fine. But it means the nucleus is still actively outgassing volatiles that should have been depleted during perihelion. If it's leftover ammonia from earlier, then something is shielding it from UV destruction, which is unusual. The spectral data also revealed fine structure in the emission lines themselves. Most cometary emission lines are broad, smeared out by the Doppler shifts caused by gas molecules moving at different velocities as they expand away from the nucleus. But several of the lines in 3I Atlas's spectrum, particularly the carbon monoxide and ammonia features, were narrower than expected, suggesting that the gas was expanding more slowly or more uniformly than thermal models predicted. Dr. Carla Reyes ran simulations testing whether coma geometry could produce narrow emission lines. If the gas was being released from a small localized region, rather than from the entire nucleus surface, the expansion velocity distribution would be narrower. But localized release should produce asymmetric coma structure, and imaging observations showed no strong asymmetry. Another possibility was that the gas was cooler than expected. Gas temperature affects line width. Cooler gas moves more slowly, producing narrower spectral lines. But cooling the gas required either a very recent release from the nucleus or some mechanism for removing kinetic energy as the gas expanded. Neither explanation fit easily with the observed outgassing rates. By November 22, Kurosawa's team had compiled a compositional inventory of 3 Atlas based on the JWST data and cross-referenced it with all available ground-based observations from September through November. The inventory showed water vapor, dominant, stable abundance, carbon monoxide, 10% of water, stable ratio, methane, 1% of water, stable ratio, ammonia, present, increasing post-perihelion, crystalline silicates, present, increasing post-perihelion, polycyclic aromatic hydrocarbons, faint but confirmed. Each component was consistent with cometary composition, but the proportions, the stability, and the post-perihelion emergence of certain features suggested that the nucleus was not simply responding to solar heating. It was releasing material in a way that appeared structured, as if layers were being exposed sequentially, or as if subsurface reservoirs were being tapped in a controlled manner. No one is claiming technology, Kurosawa emphasized in a November 24 interview. But we are seeing compositional behavior that standard thermal models struggle to explain. The chemistry is real, the timing is unusual, and we need to understand why. Structured release could be natural. Comets are layered objects, built up over millions of years from accreting ice and dust in the protoplanetary disk. If 3I Atlas formed in an environment with episodic accretion, periods of intense dust deposition, followed by periods of ice accumulation, the nucleus could have compositional layers that sublimate at different rates, producing the observed stability in outgassing ratios. But layered structures should still respond to solar heating in predictable ways. The layers closest to the surface should vaporize first, followed by deeper layers as heat conducts inward. The result should be a changing composition as different layers are exposed, not the stable ratios observed. Dr. Michael Okoye at MIT proposed an alternative. The nucleus might be a rubble pile, a loosely bound collection of smaller fragments rather than a solid body. In a rubble pile, voids and gaps between fragments create thermal insulation, slowing heat conduction and allowing subsurface ice to survive longer. Outgassing from a rubble pile could be more prolonged and more stable than outgassing from a solid nucleus. But rubble piles typically produce irregular rotation and episodic outbursts as internal voids collapse or fragments shift. 3I Atlas showed neither. Its rotation, though changed post-perihelion, was stable in November. Its outgassing was steady, not episodic. On November 25, Kurosawa submitted a follow-up paper to the journal Nature Astronomy, summarizing the JWST findings and the compositional anomalies. The paper was careful, methodical, and deliberately restrained in its conclusions. The observed composition and outgassing behavior of 3 Atlas suggests processes not fully captured by current thermal models. Further observations are required to determine whether these processes are consistent with known cometary physics or indicate novel mechanisms. The phrase, novel mechanisms, was intentionally vague. It did not specify what those mechanisms might be: exotic ices, unusual internal structure, or something else entirely. But it acknowledged that the data was pushing the boundaries of existing understanding. The composition that arrived late was not a single anomaly. It was a pattern. Crystalline silicates appearing post-perihelion. Ammonia increasing rather than decreasing. Stable outgassing ratios, despite changing solar distance. And narrow emission lines suggesting cooler, slower gas expansion than thermal models predict. Ratios suggest controlled release rather than thermal boiling. No one claimed technology, but no one could rule out structure. By late November, the chemistry of 3 Atlas had become as puzzling as its rotation and its tail. The object was behaving like a comet, but a comet with internal organization, layering, or processes that standard models had not anticipated. The clock was running. The chemistry was arriving. And the schedule was wrong. Chapter 8, November 25th, 2025. Human friction. Science does not happen in a vacuum. It happens in a world of budgets, politics, competing priorities, and institutional inertia. By late November 2025, the anomalies surrounding 3 Atlas were no longer just a scientific puzzle. They were becoming an administrative problem. Telescope time was limited. Funding was finite. And not everyone agreed that one interstellar comet, however unusual, deserved the level of attention it was receiving. On November 25th, Dr. Elena Vasquez received an email from the European Space Agency's Science Directorate informing her that her request for additional observation time on the Very Large Telescope had been denied. The reason was blunt: limited availability and higher priority targets. Vasquez had requested 12 hours of LT time in early December to conduct follow-up photometry and spectroscopy of 3 Atlas, specifically targeting the rotation anomaly and the persistent tail structure. Her proposal emphasized the object's interstellar origin, the unusual post-perihelion behavior, and the narrow window before the object became too faint for detailed study. She argued that the observations were time-critical and scientifically justified. The review panel disagreed. They said the initial observations had been sufficient to characterize the object, Vasquez explained in a recorded interview on November 27. They acknowledged the anomalies but noted that other proposals, exoplanet transits, high redshift galaxies, supernova follow-up, had clearer scientific deliverables and broader community interest. Essentially, 3 Atlas was deprioritized. This was not malice. It was triad. Telescope time is one of the most contested resources in astronomy. Every major observatory receives far more observation proposals than it can accommodate. Review panels must weigh scientific merit, feasibility, community impact, and opportunity cost. A 12-hour observation of 3 Atlas meant 12 hours, not spent on something else. And in the hierarchy of astronomical priorities, a single unusual comet, however intriguing, competed against entire research programs with years of investment and dozens of collaborators. But the decision frustrated Vasquez and others who believed the object deserved more scrutiny. "We are observing something we have never seen before," she wrote in an appeal email to the Velte Allocation Committee. "An interstellar comet exhibiting post-perihelion behavior inconsistent with models. If we do not study it now, while it is still observable, the opportunity will be lost permanently. This is not just another comet. This is a test of whether our understanding of cometary physics is complete." The appeal was acknowledged but not reversed. Similar tensions were playing out across the global astronomy community. Dr. Lina Kurosawa's proposal for a second GOST observation of 3 Atlas, submitted on November 14th, was placed in a queue behind competing requests for telescope time. JWST's schedule was planned months in advance, and inserting new targets required either displacing already approved observations or finding gaps in the schedule where the telescope's pointing constraints aligned with the target's position. By late November, the GWST scheduling team had identified a possible 4-hour window in early December. But Kurosawa was warned that the observation might be delayed or canceled if higher priority targets became available. "We are not guaranteed anything," she noted in a November 28 status update to her collaborators. "We are on the list, but we are not at the top." Funding was another constraint. Observing campaigns require money. For telescope time, data processing, travel to observatories, and researcher salaries. Most astronomy projects are funded through multi-year grants awarded by government agencies like NASA, the European Space Agency, or the National Science Foundation. These grants are competed for, peer-reviewed, and allocated years in advance, based on proposed research plans. 3i Atlas had not been part of anyone's research plan. Its discovery in June 2025 had been serendipitous, detected by the Atlas Survey Network during routine sky monitoring. Follow-up observations in July, August, and September had been conducted using discretionary telescope time, small allocations set aside for transient or unexpected targets. But as the object's anomalies became apparent, the discretionary time was exhausted, and researchers were forced to request additional funding through emergency or target of opportunity mechanisms. These mechanisms exist, but they are not generous. Dr. James Hartley at the University of Maryland submitted a target of opportunity proposal to NASA's Planetary Science Division in early November, requesting $60,000 to support additional spectroscopy, data analysis, and modeling of 3 Atlas through the end of the year. The proposal outlined the rotation anomaly, the tail persistence, and the compositional discrepancies, and argued that the object represented a high-value scientific target with implications for understanding interstellar comet populations and contemporary physics. On November 26, Hartley received a response. The proposal had been reviewed and deemed scientifically interesting, but not critical. Funding was declined. Not critical, Hartley said in a November 28 email to colleagues. An interstellar object behaving in ways we cannot explain. And it is not critical. I understand budget constraints. I understand priorities. But this feels like we are letting something important slip away because it does not fit neatly into existing program structures. The frustration was not universal. Some researchers viewed the denial of additional telescope time and funding as appropriate caution. Dr. Alan Moss, a cometary physicist at Caltech, who had not been directly involved in the 3 Atlas observations, argued in a November 27 blog post that the community was over-interpreting limited data and risking credibility by chasing ambiguous anomalies. We have seen unusual comets before, Moss wrote. We have seen objects that do not fit models perfectly. That does not mean something extraordinary is happening. It means our models are incomplete, or that the object has properties we have not yet measured. Allocating scarce resources to chase every statistical outlier is not sustainable. We need discipline. The debate spilled into public forums. Science journalists covering 3i Atlas noted the tension between researchers pushing for more observations and institutions hesitant to commit resources. Articles in Sky and Telescope, Nature News, and Scientific American framed the story as a clash between scientific curiosity and institutional pragmatism. But beneath the administrative friction was a deeper question. How much evidence is enough? At what point does an anomaly justify disrupting schedules, reallocating funds, and prioritizing one target over all others? The answer was not obvious, and different scientists had different thresholds. Dr. Carla Reyes, who had been tracking the outgassing and composition anomaly since October, believed the evidence was already compelling. We have rotation changes without torque, tail persistence without adequate energy input, and post-perihelion chemistry that defies thermal models, she said in a November 29 teleconference. Each anomaly individually might be explainable with creative modeling, but together they form a pattern. We are not chasing noise. We are tracking a signal. Dr. Yuki Tanaka was more cautious. The signal is real, he acknowledged in the same teleconference, but we do not yet know what it signifies. It could be natural processes we do not fully understand. It could be measurement errors or observational biases. More data would help, but I understand why institutions are hesitant to commit without clearer evidence of something truly unprecedented. Meanwhile, planetary defense priorities were consuming attention and resources. In late November, NASA's Planetary Defense Coordination Office announced that a newly discovered near-Earth asteroid, designated 2025 WX, would pass within lunar distance in mid-December. The asteroid posed no impact risk, but required urgent tracking to refine its orbit and assess long-term threat potential. Telescope time at several major observatories was redirected to 2025 WX, further squeezing availability for 3I Atlas observations. Planetary defense is non-negotiable, said Dr. Lindley Johnson, NASA's Planetary Defense Officer, in a November 28 press briefing. When we identify an object that could, in principle, pose a future impact risk, we track it. That is our mandate. I understand that other objects, like 3I Atlas, are scientifically interesting, but threat assessment comes first. The result was a patchwork of observations. Some researchers, like Vasquez and Kurosawa, continued working with whatever telescope time they could secure, cobbling together data from smaller observatories and lower priority instruments. Others, like Hartley, focused on analyzing existing data, refining models, and preparing publications. And a few, like Dr. Sofia Mendez, used personal telescope time allocations, hours earned through prior successful proposals, to continue tracking 3 Atlas independently. I used 2 nights of my own time at Cerro Tololo in late November, Mendez said in a December interview. Not because I was funded to do so, not because my institution asked me to, but because I believed the object was important and someone needed to keep watching. By the end of November, the observation campaign for 3 Atlas was fragmented, under-resourced, and running on the determination of individual scientists rather than coordinated institutional support. The data was still being collected. The anomalies were still being documented. But the system was straining. Budget freezes, telescope time reallocations, and planetary defense priorities clashed. Scientists pushed for more data while agencies hesitated. The mystery deepened, not because answers were hidden, but because resources were finite. Chapter 9, December 2nd, 25, the second acceleration event. Trajectory is truth. In the vacuum of space, an object's path is determined by gravity and momentum. Deviations from that path require force, solar radiation pressure, outgassing jets, or gravitational perturbations from nearby bodies. These forces are measurable, predictable, and constrained by physics. When an object deviates without an obvious force, astronomers notice. On December 2nd, 2025, 3/8, Dr. Marcus Hale at NASA's Deep Space Network had resumed radio tracking of 3I Atlas in mid-November, after the solar conjunction blackout ended. The DSN antennas in California, Spain, and Australia were once again able to lock onto the object's faint reflected radio signal and measure its Doppler shift, the tiny change in frequency caused by the object's motion toward or away from Earth. Doppler tracking is extraordinarily precise, capable of measuring velocity changes as small as millimeters per second over days or weeks. The September baseline had established 3 Atlas's trajectory with high confidence. The object was on a hyperbolic orbit, moving outward from the Sun at a velocity that would carry it back into interstellar space. Non-gravitational acceleration, the subtle push from outgassing jets, had been detected in September and quantified at approximately 2.3 times 10 to the -8 astronomical units per day squared. Small, but consistent with active comets. By late November, as tracking resumed, Hale expected the non-gravitational acceleration to have decreased. Outgassing typically declines as a comet recedes from the Sun, and with it, the jet thrust that nudges the trajectory. The acceleration should have been weaker than in September, possibly undetectable, depending on how quickly the outgassing faded. It was not weaker. It was stronger. The Doppler data from November 18th through December 1st showed a persistent velocity deviation, a small but measurable change in the object's speed that could not be explained by gravity alone. The deviation was consistent with a non-gravitational acceleration of approximately 3.1 times 10 to the -8 O per day squared, 35% higher than the September measurement. Hale ran the data through multiple processing pipelines, checked for instrumental errors, and cross-referenced the measurements with optical astrometry from ground-based telescopes. The result was consistent. The object was accelerating more than it had been before perihelion, not less. This does not fit the thermal outgassing profile, Hale noted in a December 3rd research memo. If outgassing were the cause, we would expect the acceleration to peak near perihelion and decline as the object moves away from the Sun. Instead, we are seeing an increase. Either the outgassing is intensifying post-perihelion, which contradicts thermal models, or another force is acting on the object. NCNT. Non-gravitational acceleration in comets is typically attributed to the rocket effect of outgassing jets. Gas molecules ejected from the nucleus carry momentum, and by Newton's third law, the nucleus recoils in the opposite direction. The magnitude of the acceleration depends on the mass of the nucleus, the rate of gas production, and the direction of the jets. For symmetric outgassing, gas ejected uniformly from the entire surface, the accelerations cancel out, and no net force results. But if the jets are asymmetric, concentrated on one hemisphere, a net thrust is produced. Asymmetric jets are common. Comets rotate, and as they do, different regions of the surface rotate into and out of sunlight, creating jets that turn on and off with the rotation period. The result is a pulsed thrust that, over time, averages out to a small but measurable acceleration. For 3I Atlas, the observed acceleration in December was not aligned with the Sun. If solar heating were driving the jets, the acceleration should have been primarily radial, pointing away from the Sun in the direction of the strongest thermal gradient. But the Doppler data and optical astrometry together indicated that the acceleration had a tangential component, perpendicular to the Sun-comet line. Tangential acceleration is less common, but not impossible. It can occur if the jets are oriented at an angle to the Sun-comet line, perhaps due to topography on the nucleus, cliffs, craters, or rifts that channel gas in specific directions. But the magnitude and timing of the tangential acceleration were unusual. Dr. Elena Vasquez reviewed Hale's data and compared it to her own rotation period measurements from early November. The rotation period had changed by 8% between September and November, suggesting some torque had been applied during perihelion. Torque from jets and linear acceleration from jets are related. Both depend on the same outgassing, so an increase in acceleration should correspond to an increase in torque and further rotation changes. But the rotation period in December remained stable at 16.5 hours. No additional change was detected. We have acceleration without additional rotation change, Vasquez noted in a December 4th email to collaborators. That implies the jets producing the acceleration are aligned with the rotation axis, so they produce thrust, but not torque. But jets aligned with the rotation axis should be symmetric, and symmetric jets should not produce net acceleration. We are caught in a logical loop. Dr. Yuki Tanaka's team ran simulations testing whether specific nucleus geometries could produce the observed pattern. They modeled elongated nuclei, contact binaries, and nuclei with polar jets, all configurations that could, in principle, produce linear acceleration without changing rotation. Some models fit the data, but only if the nucleus had a very specific shape and very specific jet orientations. The probability of such a configuration arising naturally was low, though not impossible. On December 5th, Dr. James Hartley at the University of Maryland published a preprint analyzing the acceleration anomaly in the context of the other observed features: tail persistence, rotation change, and compositional evolution. He calculated the cumulative probability of all observed anomalies occurring together in a single object, assuming they were independent and each explicable by natural processes. The probability was less than 1 in 20,000. Rare does not mean impossible, Hartley wrote in the preprint's conclusion. But it demands attention. We are observing a combination of features: persistent tail, rotation change, compositional stability, and now acceleration increase, that individually strain standard models and collectively form a pattern inconsistent with typical cometary behavior. Further observations are essential to determine whether these features are causally related or merely coincidental. The phrase less than 1 in 20,000 circulated quickly through the planetary science community. Some researchers viewed it as a compelling argument for extraordinary attention. Others criticized it as statistical overreach, noting that the calculation assumed independence between anomalies, which might not be valid. If the anomalies were related, if, for example, they all stemmed from a single unusual internal structure, then the combined probability was not as low as Hartley calculated. But the debate over statistics did not change the observational fact. The object was accelerating more in December than it had been in September, even though solar heating had decreased. This was the second clear deviation from expected behavior, following the rotation change documented in early November. Acceleration events had precedent. The most famous example was Onai Oumuamua, the first confirmed interstellar object, which also exhibited unexplained acceleration as it left the solar system in 2017. Multiple hypotheses had been proposed to explain Oumuamua's acceleration: outgassing, solar radiation pressure on a highly reflective surface, even a light sail, but none were definitively confirmed before the object became too faint to observe. 3. Atlas was brighter and closer than Oumuamua had been, providing better data quality. But the same ambiguity remained. Acceleration without obvious cause could be natural, exotic, or instrumental. Determining which required more observations, more modeling, and more time. Dr. Lina Kurosawa, analyzing the GGOST spectroscopy data, noted that the observed outgassing rates in mid-November were consistent with the non-gravitational acceleration measured in September, but not with the higher acceleration measured in December. If the acceleration is due to outgassing, the gas production rate must have increased by 35% between September and December, she said in a December 6th analysis. But the spectroscopy shows stable or slightly declining gas production. The numbers do not align. One possibility was that the outgassing had become more directional, not increasing in total amount, but more focused, producing more thrust per unit of gas ejected. This could happen if vents or jets on the nucleus narrowed over time, collimating the gas flow. But collimation typically occurs as surface layers erode and subsurface pressures change, processes that should be most intense during perihelion, not after. Another possibility was that the acceleration was not from outgassing at all. Solar radiation pressure, though weak, could produce small accelerations if the object's reflectivity changed. If, for example, the surface brightened as fresh ice was exposed, or darkened as dust accumulated. But radiation pressure accelerations scale with surface area and albedo, and no significant brightness changes were observed between September and December. A third possibility, rarely spoken aloud, was that the acceleration was not natural. On December 7th, Dr. Sofia Mendes sent a private email to a small group of colleagues. I know we avoid this conversation, but if we are scientists, we must consider all hypotheses consistent with the data. The acceleration is real. The timing is unusual, and the lack of a clear thermal explanation is troubling. I am not claiming anything extraordinary. I am asking whether we have ruled it out. The email was not widely shared, but it reflected a growing unease within the observation team. The stack of anomalies was growing. Each individually could be explained with effort, but together they formed a pattern that felt less like coincidence and more like signal. Stacked odds now moved from coincidence toward pattern. Tracking showed a subtle but measurable velocity deviation, not aligned with solar radiation pressure. Chapter 10. December 7th, 2025. When models start disagreeing. Science progresses through consensus, but consensus is earned through debate. When the same data produces different conclusions in the hands of different researchers, the debate becomes visible, and sometimes uncomfortable. By early December 2025, independent teams analyzing 3E Atlas were arriving at fundamentally different interpretations of what the object was and what its behavior meant. On December 7th, two preprint papers appeared on the ArcSevi repository within hours of each other, both analyzing the same datasets, both peer-reviewed by the same observational community, and both reaching opposite conclusions. The first paper, led by Dr. Yuki Tanaka at Kyoto University, was titled Post-Perihelion Activity of 3I Atlas, a natural comet with complex internal structure. The paper argued that all observed anomalies, the tail persistence, rotation change, compositional stability, and acceleration increase, could be explained by a rubble pile nucleus with high porosity, layered composition, and delayed subsurface outgassing. The models Tanaka's team constructed were detailed, running thermal evolution simulations forward from the September baseline through perihelion and into December, testing thousands of configurations until they found parameter sets that matched the yacht observations. Our models demonstrate that a porous, layered nucleus can produce extended outgassing activity post-perihelion due to slow thermal conduction and delayed sublimation of subsurface ices, Tanaka wrote in the abstract. The observed rotation change is consistent with torque from asymmetric jets active during perihelion, and the observed acceleration increase is consistent with the exposure of fresh, volatile-rich material in December. While unusual, the behavior of 3 Atlas is within the range of natural cometary variability. The second paper, led by Dr. James Hartley at the University of Maryland, was titled Anomalous Behavior of 3E Atlas: Observational Constraints and Open Questions. Hartley's paper took a more agnostic stance, cataloging the anomalies without committing to a specific explanation. It systematically tested multiple hypotheses: rubble pile structure, exotic ices, subsurface voids, radiation pressure effects, and concluded that none fully explained the data without requiring improbable parameter choices. While natural explanations remain possible, they require assumptions about the nucleus's structure and composition that are not independently verifiable, Hartley wrote. The cumulative probability of the observed features occurring together in a single object is low, suggesting either that 3I Atlas is an extremely rare comet or that our models of cometary physics are incomplete in ways not yet understood. The difference between the two papers was subtle but significant. Tanaka's team had found a model that worked. Hartley's team questioned whether that model was justified. The disagreement was not about the data. Both teams used the same observations, the same photometry, the same spectroscopy, the same Doppler tracking. The disagreement was about interpretation. How many assumptions were acceptable? How much flexibility in model parameters was reasonable? And at what point did fitting the data become forcing the data to fit? Dr. Elena Vasquez, who had been collaborating with both teams, found herself in the middle of the debate. Yuki's models are rigorous, she said in a December 9th teleconference. They work mathematically, but they require the nucleus to have very specific properties: porosity in a narrow range, layering with precise volatile gradients, jet orientations that align almost perfectly with the rotation axis. If you change any of those parameters by even 10 or 20%, the model stops matching the data. That makes me uncomfortable. Nature is not usually that precise. Tanaka defended his approach. All models require assumptions, he replied in the same teleconference. The question is whether the assumptions are physically plausible. High porosity is observed in other comets. Layered composition is consistent with formation models. Asymmetric jets are common. Yes, the parameter space is narrow, but narrow does not mean impossible. We have found a natural explanation. That should be the default until proven otherwise. Mineral and Yemen. Hartley pushed back. The default should be the simplest explanation consistent with the data. But if the simplest explanation requires a long chain of specific, unverifiable assumptions, is it still simple? I am not arguing for exotic hypotheses. I am arguing that we do not yet have enough information to choose between competing natural explanations with confidence, and that claiming confidence prematurely risks missing something important. The debate played out in email threads, teleconferences, and comment sections beneath the preprint papers. Other researchers weighed in. Some sided with Tanaka, emphasizing the importance of exhausting natural explanations before considering alternatives. Others sided with Hartley, emphasizing the importance of intellectual humility when confronted with ambiguous data. Dr. Carla Reyes at the University of Arizona argued for a middle path. Both papers are correct within their own frameworks, she said in a December 10th blog post. Tanaka has shown that natural processes can, in principle, explain the observations. Hartley has shown that those explanations are not uniquely constrained by the data. The disagreement is not scientific. It is philosophical. Do we privilege models that fit or models that predict? Do we value explanatory power or parsimony? But the philosophical disagreement had practical consequences. Telescope, time allocation committees, funding agencies, and mission planning boards all relied on scientific consensus to guide decisions. If the community was divided on whether 3I Atlas was a typical comet with complex structure or an atypical object requiring further scrutiny, those divisions influenced whether additional resources were allocated. On December 8th, Dr. Lina Kurosawa's request for a second GGOSD observation was reviewed by the Space Telescope Science Institute's Director's Discretionary Time Committee. The committee had access to both Tanaka's and Hartley's preprints and asked Kurosawa to justify why additional observations were necessary, given that Tanaka's models had already provided a natural explanation. "Models are not observations," Kurosawa replied in her justification statement. Tanaka's work demonstrates that natural explanations are possible. But possibility is not confirmation. A second GUSD observation would allow us to test whether the compositional trends we observed in November are continuing, which would constrain the thermal models and potentially discriminate between competing hypotheses. Without that data, we are arguing over models, not testing them. The committee approved 4 hours of telescope time for mid-December, contingent on scheduling constraints. It was less than Kurosawa had requested, but it was something. The disagreement extended to the public sphere. Science journalists covering 3I Atlas struggled to convey the nuance of the debate. Headlines oscillated between mysterious interstellar comet, explained, and scientists baffled by rogue objects' behavior, depending on which paper the journalist had read first and which researcher they had interviewed. Dr. Alan Moss at Caltech, who had been critical of the observation campaign's intensity, published an editorial in Nature on December 9th titled "The Danger of Anomaly Hunting." The editorial argued that the astronomy community was at risk of over-interpreting noise, driven by the media attention surrounding interstellar objects and the unresolved questions from Ona I Youmuama. "Every comet is unique," Moss wrote. "Every comet deviates from models in some way. That is not evidence of new physics or extraordinary phenomena. It is evidence that comets are complex, and our models are approximations. The debate over 3E Atlas is not about the object. It is about our expectations. We expected another Oumuamua-level mystery. And when the data did not immediately provide one, we invented it by stacking ambiguous anomalies and calling the stack significant. The editorial was widely read and widely criticized. Dr. Sophia Mendes responded with a letter to Nature arguing that Moss's dismissal was premature. "Anomaly hunting is how science progresses," she wrote. "Uranus's orbit was an anomaly until Neptune was discovered. Mercury's perihelion precession was an anomaly until general relativity explained it. Dismissing anomalies as noise is as dangerous as over-interpreting them. The responsible path is continued observation and open debate, not premature closure." Meanwhile, independent modelers outside the core observation team began running their own simulations. Dr. Patricia Nguyen at the Australian National University used a different thermal model framework than Tanaka's team, and found that she could not reproduce the December acceleration increase without invoking either a change in the nucleus's albedo or a concentrated jet that was not active in September. Neither option was observationally supported. "I trust Tanaka's work," Annie said in a December 11th email to colleagues. "But I cannot get the same results using my code. That suggests either his model has parameter degeneracies, multiple configurations produce similar outputs, or that the solution is sensitive to assumptions embedded in his framework but not in mine. Either way, the model is not robust." Robustness is a key test for scientific models. A robust model produces consistent results across different implementations, different initial conditions, and different parameter choices. A fragile model works only under specific conditions and breaks when those conditions are perturbed. Fragile models can be correct, but they require more evidence to be convincing. By mid-December, the scientific community had not reached consensus. Tanaka's natural explanation had adherents. Hartley's agnostic caution had adherents. And a smaller, quieter group, including Mendez, Kurosawa, and Vasquez, was beginning to consider that the anomalies might be pointing towards something genuinely novel, though they were reluctant to specify what. "I do not know what is happening with this object," Vasquez said in a December 12th interview. "I know the data is real. I know the models are struggling. And I know that we are in the uncomfortable position of having more questions than answers. That is not failure. That is science working as it should. But it is frustrating when the system, the telescopes, the funding, the allocation committees, demands certainty before committing resources. Certainty is what we are trying to reach. We are not there yet." The models were disagreeing. The researchers were disagreeing. And the object, indifferent to human debate, continued outward into the dark, carrying its anomalies with it. This chapter lived inside the scientific argument itself. Uncertainty became visible. Independent teams ran the same data and got different conclusions. Chapter 11, December 12, 2025. The Probability Wall. Statistics are cold comfort when the numbers turn hostile. Probability is the language science uses to separate signal from noise, pattern from coincidence, and meaningful from random. By mid-December 2025, the cumulative probability of 3 in Atlas's observed anomalies was forcing uncomfortable conversations. On December 12th, Dr. James Hartley's research group at the University of Maryland published an expanded analysis, quantifying the likelihood of each observed anomaly occurring individually, and then compounding those probabilities to estimate the likelihood of all anomalies occurring together in a single object. The analysis was methodical. Hartley's team began by defining baseline expectations for cometary behavior using archival data from over 200 well-studied comets observed during close solar approaches. They calculated the distribution of tail persistence durations, rotation period changes, compositional stability, and non-gravitational acceleration profiles. These distributions established what was typical, what was rare, and what was extremely rare. For tail persistence, they found that fewer than 8% of comets showed tail brightness retention beyond 3 weeks, post-perihelion, at levels greater than 30% of peak brightness. 3. Atlas, at 40% brightness 4 weeks, post-perihelion, fell into the rarest 5% of that distribution, a 1 in 20 occurrence. For rotation period, changes without detectable torque sources, the data was sparser because few comets had been monitored with sufficient precision to detect small rotation changes. But among the 30 comets with high-quality rotation measurements before and after perihelion, only 2 showed changes greater than 5% without corresponding asymmetric jet activity. That placed 3I Atlas in the top 7% of unusual rotation behavior, roughly 1 in 14. For compositional stability across perihelion, the baseline was even more limited. High-resolution spectroscopy of the same comet before and after perihelion was rare. And most observations showed significant variation in volatile ratios as different surface regions activated. Of the 12 comets with comparable spectroscopy, only 1 showed ratio stability within 5%, similar to 3 Atlas. That was 1 in 12. For non-gravitational acceleration increasing post-perihelion, rather than decreasing, no direct precedent existed in the archival data. Every well-tracked comet showed declining acceleration as it receded from the Sun. Hartley's team assigned this anomaly a conservative probability of 1 in 50, acknowledging that the true rarity could be higher but lacking data to quantify it precisely. The combined probability, assuming independence, was the product of these individual probabilities, 1 in 20 times 1 in 14 times 1 in 12 times 1 in 50. The result was approximately 1 in 168,000. But independence was questionable. If the anomalies were causally related, if they all stemmed from a single unusual property of the nucleus, such as extreme porosity or layered volatile distribution, then the combined probability was not the product but something higher. Hartley's team tested correlated models, where the anomalies were assumed to share a common cause, and found combined probabilities ranging from 1 in 5,000 to 1 in 50,000, depending on assumptions. Even the most generous correlated estimate placed 3E Atlas in the rarest fraction of a percent of observed comets. Rare does not mean impossible, Hartley wrote in the paper's discussion section. Nature produces outliers. Extremes exist, but outliers demand scrutiny. When an object falls into the tail end of multiple independent distributions simultaneously, we must ask whether we are observing natural variability or whether our baseline assumptions are flawed. The phrase probability wall emerged in discussions among the research team. It referred to the point at which cumulative improbability becomes difficult to dismiss as coincidence and begins to suggest either that the baseline model is wrong or that the object is genuinely exceptional in ways not previously encountered. Dr. Elena Vasquez reviewed Hartley's statistical analysis and raised a methodological concern. The baseline we are using, archival comet data, is biased toward solar system comets, she noted in a December 13th email. 3 Atlas is interstellar. If interstellar comets formed under different conditions, in different stellar environments, with different compositions or structures, then comparing them to solar system comets may not be valid. We might be calculating the probability of a solar system comet behaving like 3E Atlas, when the relevant question is the probability of an interstellar comet behaving this way, and we have no baseline for that. Hartley acknowledged the concern. You are right, he replied. Our baseline is imperfect, but it is the only baseline we have. We have observed exactly 3 interstellar objects, Oumuamua, Borisov, and 3I Atlas. That is not enough to define a separate statistical distribution. So we compare to what we know, with the caveat that interstellar objects may not follow the same rules. But if they do not, that itself is significant. The debate over whether 3I Atlas should be compared to solar system comets or treated as a separate category reflected a deeper uncertainty. How different could interstellar objects be and still be called comets? If every interstellar comet behaved unusually compared to solar system comets, then unusual would simply be the interstellar norm, and no anomaly would be surprising. But if interstellar comets were supposed to follow the same physics, the same thermodynamics, the same sublimation behavior, the same response to solar heating, then deviations required explanation. Dr. Yuki Tanaka, whose models had provided a natural explanation for the anomalies, disputed Hartley's probability calculation on different grounds. Statistics are only as good as the model used to generate them, Tanaka argued in a December 14th email thread. James is calculating the probability of the observations given standard comet models. But if the standard models are incomplete, if they do not account for high porosity, subsurface layering, or delayed outgassing, then the calculated probabilities are artificially low. A better approach is to calculate the probability given updated models that include these effects. And when we do that, the observations are not improbable at all. Hartley countered that updating models to fit observations and then using those updated models to calculate probabilities was circular reasoning. You cannot fit the data and then claim the fit was probable, he wrote. Probability must be calculated against a baseline established before the observations, not after. Otherwise, you are just claiming that anything you can model is probable, which renders the concept of improbability meaningless. The exchange was respectful but tense, reflecting a fundamental tension in how science handles anomalies. Do you expand the model to accommodate the data, or do you question whether the data is telling you the model is wrong? On December 15th, Dr. Carla Reyes convened a virtual meeting of the core observation team to discuss the statistical findings and their implications for future observation strategy. 23 researchers joined the call, representing institutions across North America, Europe, Asia, and Australia. We are at a decision point, Reyes said in her opening remarks. The object is getting fainter. It is moving farther from the sun and farther from Earth. Within weeks, It will be too faint for detailed spectroscopy or precise photometry. We are running out of time, and we need to decide whether the statistical case James has made is compelling enough to justify a more intensive, coordinated observation campaign, or whether we accept Yuki's natural explanation and move on. The discussion that followed was revealing. Roughly half the participants believed that Tanaka's models were sufficient, and that further observations, while scientifically interesting, were not urgent. The anomalies were explainable, even if the explanations required specific assumptions. Absent evidence of something truly unprecedented, something that could not be explained by natural processes, additional resources were hard to justify. The other half believed that the probability analysis was troubling, and that the narrow window remaining before the object became unobservable made immediate action essential. Even if natural explanations were possible, the cumulative improbability and the lack of independent verification for the model assumptions warranted more data. Science does not operate on probability thresholds, said Dr. Michael Okoye, summarizing one side of the debate. We do not declare something extraordinary just because it is improbable. We require evidence, and so far, all the evidence is consistent with natural, if unusual, cometary behavior. But science also does not ignore warning signs, countered Dr. Sofia Mendes. When an object falls into the extreme tail of every distribution we measure, that is a warning sign. Maybe it is natural. Maybe it is a fluke. But maybe it is something we have not seen before. And if we do not look now, we will never know. The meeting ended without consensus. Observation plans would continue on an ad hoc basis, with individual researchers pursuing whatever telescope time and funding they could secure independently. There would be no coordinated campaign, no emergency reallocation of resources, no institutional commitment to intensive study. We are doing science by patchwork, Vasquez said after the meeting ended. And patchwork might be enough. Or it might mean we missed something important, because no single observer had the full picture. By the end of December 12th, the probability wall was documented, debated, and unresolved. The numbers were real. The interpretation was not agreed upon. And the object continued to move, indifferent to human uncertainty, carrying its improbable combination of features deeper into the outer solar system. Combined anomalies pushed statistical likelihoods into uncomfortable territory, less than 1 in 20,000 under standard comet assumptions. Rare does not mean impossible, but it demands attention. Chapter 12. December 19, 2025. After the sun let go. There is a line in space, invisible but precise, where the sun's influence transitions from dominant to secondary. For 3I, Atlas, that line was crossed on December 19, 2025, 1 month after perihelion, at a distance of 0.84 astronomical units from the sun. Beyond this point, solar radiation pressure, solar wind interaction, and direct thermal heating all fell below the thresholds needed to drive the vigorous outgassing and activity observed in October and November. On this date, the sun let go, and the anomalies continued. The calculation was straightforward. Dr. Yuki Tanaka's thermal models predicted that at 0.84 outbound, surface temperatures on the nucleus should have dropped to approximately 250 Kelvin, well below the sublimation temperature of water ice under vacuum conditions. Residual heat from perihelion could persist in subsurface layers for days or weeks, but only in the top few centimeters. Deeper ice, which had never been directly heated, would remain cold and inert. Outgassing should have declined sharply, approaching background levels consistent with distant, dormant comets. It did not. On December 20th, Dr. Lina Kurosawa obtained the second WSD observation of 3 Atlas using the 4 hours of director's discretionary time approved in early December. The MIRI spectrograph once again locked onto the object, now significantly fainter than in November, but still detectable across mid-infrared wavelengths. The spectrum showed persistent emission from water vapor, carbon monoxide, and ammonia, not at November levels, but far higher than thermal models predicted for an object at 0.840 with a month of cooling behind it. The crystalline silicate features identified in November were still present, slightly weaker, but unmistakable. and the polycyclic aromatic hydrocarbons, faint in November, remain detectable in December. This is not residual heat, Kurosawa said in a December 22 analysis briefing. At this distance, and this far post-perihelion, the thermal gradient between the Sun and the nucleus is too shallow to drive significant sublimation. Surface ice that was going to vaporize already did so during perihelion. What we are seeing now requires either a continuous resupply of fresh volatiles from the interior, or an energy source independent of direct solar heating. The first option, continuous resupply, was physically plausible. If the nucleus had deep fractures or voids that connected the surface to volatile-rich subsurface reservoirs, gas could seep outward over time, sustained by pressure differences rather than temperature gradients. This would explain prolonged outgassing without requiring ongoing thermal input. But continuous resupply should produce episodic bursts, not steady emission. As subsurface reservoirs vented, the pressure would drop, and the outgassing would fade until new pathways opened or new reservoirs were tapped. The steady, persistent emission observed in December suggested a more stable source. The second option, an energy source independent of the Sun, was less comfortable. What energy source? Radioactive decay was too weak to heat an object this small. Tidal heating required proximity to a massive body, and 3I Atlas was alone in space. Chemical reactions could release heat, but comets are chemically inert at these temperatures, unless the nucleus was not purely inert. Dr. Marcus Hale reviewed the December Doppler tracking data from the Deep Space Network, and confirmed that the non-gravitational acceleration was still present, not as strong as in early December, but measurable and persistent. At 0.840, with thermal activity declining, the acceleration should have been undetectable. Yet, the object was still deviating from a purely gravitational trajectory. We are observing sustained non-gravitational acceleration 3 weeks after the point where solar heating should have ceased driving jets, Hale noted in a December 21 memo. This is inconsistent with standard thermal outgassing. The jets, if that is what they are, should have turned off by now. On December 19, solar influence dropped below dominance thresholds. Yet the anomalous behaviors continued. Dr. Elena Vasquez re-measured the rotation period, using photometry obtained on December 18 with the Nordic Optical Telescope. The result was consistent with the November measurement, 16.5 hours, unchanged since early November, despite the ongoing acceleration that should have been torquing the nucleus if it was due to asymmetric jets. We have persistent acceleration without rotation change, Vasquez summarized in a December 23 email. That pattern has held since November. It suggests the acceleration is not from asymmetric jets, or if it is, the jets are oriented in a way that produces thrust without torque. Both scenarios are rare, and both require specific, unverified assumptions about the nucleus's geometry. Dr. Sofia Mendes obtained wide-field imaging of the tail on December 20th, using the Cerro Tololo Observatory. The tail was still visible, faint but structured, with a length exceeding 2 degrees of sky. For comparison, comets at similar solar distances typically showed tails less than half that length, if visible at all. The tail should be gone by now, Mendes said in a recorded interview on December 22, or at least so faint that we would not detect it without long exposures and heavy processing. But it is there. It is clear. And it is still showing internal structure, knots and streamers, that suggest active dust and gas production. This is not residual material drifting away from perihelion. This is ongoing activity. Nens. By December 24, the observation team had compiled a summary document listing all confirmed anomalies as of December 19, the date when solar dominance ceased. Tail persistence. Visible and structured tail extending 42 days post-perihelion. Brightness at 35% of peak, despite 5 weeks of declining solar heating. Rotation change. 8% increase in rotation rate between September and November, with no further change, despite ongoing acceleration. Compositional stability. Water to CO and water to methane ratios stable within 5% from September through December, inconsistent with differential sublimation. Crystalline silicates. Emission features appearing post-perihelion and persisting through December, requiring temperatures inconsistent with declining solar heating. Non-gravitational acceleration. 35% increase between September and December, persistent through December 20th, despite thermal activity decline. Each anomaly had natural explanations: complex structure, subsurface reservoirs, delayed outgassing, specific jet geometries. But the explanations required assumptions that could not be independently verified, and the cumulative probability of all anomalies occurring together remained low under any baseline model. The central claim of this documentary was distilled into a single observation. The data changed only after the sun stopped mattering. Before perihelion, 3 Atlas behaved predictably. During perihelion, it was unobservable. After perihelion, it behaved anomalously. And as solar influence declined further, the anomalies persisted rather than fading. The timeline suggested that whatever was driving the anomalies was not purely solar-driven. Dr. James Hartley articulated this in a December 26th preprint titled Post-Solar Persistence in 3A Atlas. Implications for internal energy sources. The paper did not claim to identify the energy source. It simply argued that the observed persistence required one, and that standard cometary models did not provide it. We are observing sustained activity at solar distances and post-perihelion timescales inconsistent with thermal models, Hartley wrote. Either the nucleus has an internal heat source, radiogenic, chemical, or structural, or our understanding of cometary thermodynamics is incomplete. Both possibilities warrant further investigation. The phrase internal heat source was carefully neutral. It did not specify what the source might be, natural or otherwise. But it acknowledged that the sun alone was insufficient. On December 25th, Dr. Carla Reyes published a blog post titled What 3 in the Atlas is Teaching Us About Scientific Uncertainty. She reflected on the months of observation, the debates, the statistical analysis, and the growing unease within the team. We are trained to prefer natural explanations, Reyes wrote. And that is correct. Nature is vast, complex, and capable of producing phenomena we have not seen before. But we are also trained to follow the data, even when it leads to uncomfortable places. The data on 3 Atlas is uncomfortable, not because it proves anything extraordinary, but because it does not fit comfortably into the framework we thought was complete. By December 26th, the observation window was closing. 3I Atlas was now magnitude 18, invisible light, faint enough that only large telescopes with long exposure times could detect it. Spectroscopy was becoming prohibitively difficult. Photometry was still possible but increasingly noisy. Doppler tracking would continue through January, but with lower precision as the signal weakened. The object was leaving. The sun had let go. The anomalies had not. And the questions remain. This chapter makes the central claim of the documentary. The data changed only after the sun stopped mattering. On this date, solar influence dropped below dominance thresholds. Yet the anomalous behaviors continued. Chapter 13, December 27th, 2025. What we can't say yet. Science is a discipline of restraint. It is the practice of knowing what you know, what you do not know, and where the boundary lies. By late December 2025, the observation team tracking 3 Atlas had reached that boundary. The data was recorded, the anomalies were documented, and the explanations remained incomplete. On December 27th, Dr. Elena Vasquez drafted an internal memo to the European Space Agency's Science Directorate summarizing the status of the 3I Atlas investigation. The memo was intended for program managers, not for public release, and its tone reflected the careful balance between reporting findings and avoiding premature conclusions. We have observed an interstellar comet exhibiting post-perihelion behavior inconsistent with standard thermal models, Vasquez wrote. Multiple independent observation Campaigns have confirmed persistent tail activity, compositional stability, rotation anomalies, and non-gravitational acceleration beyond the expected solar influence regime. Natural explanations involving complex internal structure, delayed subsurface outgassing, and exotic volatile compositions are possible, but require assumptions that cannot be verified with available data. We recommend continued monitoring as the object recedes, pending future mission opportunities for in situ study. So, the phrase "cannot be verified" was key. It acknowledged that the team was operating at the edge of what remote observation could achieve. They could measure brightness, spectra, and trajectories, but they could not see inside the nucleus. They could not sample the material directly. They could not distinguish between a porous rubble pile, a layered ice structure, or something more organized. Remote observation has limits. Dr. James Hartley convened a closed teleconference on December 27th with the core observation team to discuss what could and could not be stated publicly. The meeting was not about suppressing information. All data was already public and archived, but about framing conclusions responsibly. "We need to be clear about what we are claiming and what we are not claiming," Hartley said in his opening remarks. "We are not claiming that 3EI Atlas is artificial. We are not claiming that it defies known physics. We are claiming that it exhibits a combination of features rare among observed comets, and that current models struggle to explain those features without invoking specific, unverified structural assumptions." That is a scientific statement, not a sensational one. Dr. Lina Kurosawa agreed. "The moment we say we cannot explain this, the public interpretation will be aliens, and that is not what the data shows. The data shows an unusual comet. Unusual is not unexplainable. It just means we need better models, or more data, or both." Dr. Sofia Mendes raised a counterpoint. "But we also cannot say, this is definitely natural, and we understand it, because we do not. The models that fit the data require parameters we cannot verify. The probability analysis suggests the object is in the extreme tail of observed behavior. If we overstate our confidence in natural explanations, we are being as irresponsible as if we overstate the case for something exotic." Now, well, the tension in the conversation reflected a broader challenge in science communication: how to convey uncertainty without inviting misinterpretation. The public, and even many scientists outside the field, expected binary answers: natural or artificial, explained or unexplained. But the reality was more nuanced. The object was probably natural. The behavior was partly explained. And the gaps in understanding were significant, but not insurmountable. Dr. Yuki Tanaka, whose models had provided the most detailed natural explanation, emphasized the importance of not overstating the anomalies. "We have an explanation that works," he said. "It requires assumptions, yes, but all models do. Unless we have evidence that directly contradicts natural processes, and we do not, the default position must be that this is a comet with unusual but natural properties." Hartley responded carefully. "I agree that the default is natural. But defaults can be wrong. The point of observation and analysis is to test defaults, not to defend them. And right now, the data is testing our default models more than I am comfortable with. That does not mean the models are wrong. It means we need to be open to the possibility." On December 28th, the team finalized a joint statement for release to the International Astronomical Union and the broader scientific community. The statement was intentionally cautious, written to convey findings without overreach. Observational Summary of Interstellar Object, 3 Atlas, December 2025. 3 Atlas, discovered in June 2025, and confirmed as the third interstellar object detected in the solar system, has been observed extensively from July through December 25. The object exhibited active cometary behavior with a well-defined coma and tail, and passed perihelion on October 19, 2025, at a distance of 0.340 from the Sun. Post-perihelion observations have documented several features of interest: tail persistence and brightness retention beyond typical decay timescales, rotation period change between pre- and post-perihelion observations without clearly identified torque sources. Compositional stability across perihelion, inconsistent with simple thermal sublimation models. Non-gravitational acceleration, persisting beyond the regime of dominant solar thermal influence. These features are individually rare, but not unprecedented in cometary observations. Their occurrence together in a single object is statistically unusual and suggests either that 3I Atlas possesses a complex internal structure not fully characterized by current remote observation techniques, or that models of cometary thermal evolution require refinement. Natural explanations involving porous nuclei, subsurface volatile reservoirs, and delayed outgassing are consistent with the observations, but require structural assumptions that cannot be independently verified without in situ measurement. Continued ground-based and space-based observation is recommended as the object recedes. Future missions capable of rendezvous or sample return would provide definitive constraints on the nucleus's composition and structure. No evidence currently supports non-natural explanations for the observed behavior. The final sentence, no evidence currently supports non-natural explanations, was debated extensively before inclusion. Some team members felt it was unnecessary, as the entire statement was framed around natural processes. Others felt it was essential to preemptively address public speculation and media framing. We include it or the headlines will, Reyes argued. Better to control the narrative than to let it be controlled for us. The statement was released on December 29. Responses were immediate and predictable. Some media outlets emphasized the unusual features and framed the story as scientists struggle to explain mysterious interstellar visitor. Others emphasized the natural explanation framework and framed it as interstellar comets' strange behavior, likely natural, researchers say. Both framings were defensible. Both were incomplete. On December 30th, Dr. Michael Okoye published a personal reflection on the 3I Atlas investigation in a blog post titled Living with Uncertainty. He described the experience of working on an object that defied easy categorization, the intellectual discomfort of not having definitive answers, and the importance of resisting the urge to force conclusions. Science is not about certainty, Okoye wrote. It is about iteratively reducing uncertainty. We started with an interstellar comet and a baseline model. The observations challenged that model. We refined the model. The observations challenged it again. This is how science works. It is messy. It is slow. And it requires intellectual humility, the willingness to say, I do not know, when that is the honest answer. By December 31st, 3I Atlas was magnitude 19 and fading. Spectroscopy was no longer feasible with ground-based telescopes. Photometry was marginal. Doppler tracking would continue into January, but with diminishing precision. The object was slipping beyond the reach of detailed study, carrying its mysteries with it into interstellar space. The team had done what they could. The data was archived. The papers were written or in progress. The debates would continue. But the window was closing. This chapter is restraint, what science refuses to claim without proof. We cannot say this is artificial. We cannot say it is definitely natural and understood. We can only say what we observed, what we tried to explain, and where the explanations fall short, Vasquez said in a final interview on December 31st. That is not failure. That is honesty. See down. No declarations. No conclusions. Only boundaries of knowledge. Chapter 14, January 4th, 2026. The quiet that follows. Space is silent, but data tell stories long after the object is gone. By early January 2026, 3 Atlas had receded to 1.2 astronomical units from the Sun, moving outward at 36 kilometers per second, too faint for most telescopes to detect and too distant for detailed spectroscopy. The observation campaign had ended. The object was leaving, and the community was beginning to process what had been learned and what had not. On January 4th, Dr. Sofia Mendes obtained what would be the final ground-based photometric observation of 3A Atlas using the Cerro Tulo Observatory. The object was magnitude 20, at the limit of detectability even with long exposures. The light curve showed no significant variability. The rotation period, if still measurable, was too subtle to extract from the noise. The tail, if still present, was invisible. "It has gone quiet," Mendez said in a recorded note attached to the data file. "Whether that means the activity has ceased, or simply that we can no longer see it, I cannot say. But the data stabilizes here. This is where the story ends, at least from our perspective." The final Doppler tracking session from NASA's Deep Space Network was conducted on January 3rd. The signal was weak, barely distinguishable from background noise, but sufficient to confirm the object's trajectory. The non-gravitational acceleration, which had been measurable through late December, was no longer detectable. Either it had stopped, or it had dropped below the detection threshold. Dr. Marcus Hale archived the tracking data and compiled a final trajectory solution. "The object's orbit is hyperbolic as expected," he wrote in the summary. "It will exit the solar system on a path inclined 78 degrees to the ecliptic plane, moving toward a point in the constellation Lynx. It will not return, barring an unlikely gravitational perturbation. 3 Atlas will spend the rest of its existence in interstellar space, drifting through the galaxy at roughly the same velocity it had when it entered our solar system, about 26 kilometers per second relative to the local standard of rest. The object would pass beyond Neptune's orbit in approximately 2 years. Beyond the heliopause, the boundary where the sun's influence truly ends, in about 4 years. And beyond the reach of any conceivable human-made probe in the foreseeable future. It would become a point of light, then a memory, then an entry in a catalog." On January 5th, the European Space Agency's Science Directorate convened a post-campaign review meeting, attended virtually by researchers who had contributed to the 3 Atlas observation effort. The meeting was intended to assess lessons learned, identify gaps in capability, and discuss whether future interstellar object encounters should be handled differently. Dr. Elena Vasquez presented a summary of the observation timeline, highlighting the critical role of the September baseline, the impact of the conjunction blackout, and the challenges of coordinating international telescope time. "We did well with the resources we had," she said. "But we were not prepared for an object that required continuous, high-cadence monitoring across multiple wavelengths and observation types. If another interstellar object is detected with similarly unusual behavior, we need a more coordinated response." The meeting also addressed the scientific outcomes. Dr. Yuki Tanaka presented his thermal models, emphasizing that natural explanations were viable and that the object's behavior, while unusual, did not require new physics. Dr. James Hartley presented the statistical analysis, emphasizing the low probability of the observed combination of features and the need for continued theoretical work to refine cometary models. "Both perspectives are valid," said Dr. Günther Hassinger, ESA's Director of Science, in closing remarks. "This object has taught us that interstellar comets may not behave identically to solar system comets, and that our models must be flexible enough to accommodate diversity. It has also taught us that remote observation has limits. If we want definitive answers about objects like 3I Atlas, we will need missions capable of close encounter or sample return. That is not feasible now, but it should inform future mission planning." On January 7th, Dr. Lina Kurosawa submitted the final JBUST analysis paper to the Astrophysical Journal. The paper documented the November and December spectroscopy, analyzed the compositional features, and discussed the implications for interstellar comet formation environments. The conclusion was measured. 3A Atlas exhibits compositional and thermal properties consistent with a comet formed in a protoplanetary disk with different volatile abundances than the solar nebula. The post-perihelion persistence of crystalline silicates and stable volatile ratios suggest complex internal structure and warrant follow-up study if future interstellar comets are detected. The public interest in 3I Atlas began to wane in early January. News cycles moved on. The object was no longer visible. And without dramatic new findings, the story faded from headlines. A few science communicators continued to discuss the anomalies in podcasts and YouTube videos, but the tone was speculative rather than urgent. Dr. R. Alan Moss, who had been critical of the observation intensity, published a retrospective article in Sky and Telescope on January 10th, titled "What 3 Atlas Taught Us About Hype." The article argued that the object had been overinterpreted due to lingering excitement from Oumuamua, and that the scientific community had learned valuable lessons about maintaining skepticism and avoiding premature conclusions. 3 Atlas was an unusual comet, Moss wrote, but it was a comet. The anomalies, while statistically rare, were within the bounds of natural variability. The real lesson is that every object is unique, and uniqueness alone is not evidence of the extraordinary. Dr. Carla Reyes responded in a blog post, arguing that Moss's retrospective minimized the genuine challenges the data had posed. "We did not overinterpret," she wrote. "We interpreted cautiously, tested multiple hypotheses, and acknowledged the limits of our understanding. That is exactly what science should do. Dismissing the effort as hype is dismissing the process itself." By mid-January, the observation team had largely dispersed, returning to other projects and pre-existing research programs. The data would continue to be analyzed for months, possibly years, as researchers extracted additional insights, tested new models, and cross-referenced findings with future observations of other interstellar objects. But the active, real-time investigation was over. On January 12th, Dr. Sofia Mendez recorded a final personal reflection, intended for her own archive but later shared with colleagues. "I do not know what 3A Atlas was," she said. "I do not know if it was just a comet with unusual structure, or if it was something we have not encountered before. I know that it challenged me. It made me question assumptions I thought were solid. And it reminded me that the universe is under no obligation to behave in ways we find familiar." She paused, then continued. "The data stabilized. The object quieted. But the questions do not. And maybe that is the point. Science is not about having all the answers. It is about having better questions each time." As 3IS receded into the darkness between stars, the legacy of its passage was not a single answer, but a set of improved tools, refined models, and a clearer understanding of what we do not yet know. The baseline was clean. The deviations were real, and the debate would continue long after the object was gone. On January 15th, the International Astronomical Union's Minor Planet Center issued a final update on 3I Atlas, noting that the object was no longer being actively tracked, and that its designation would remain in the catalog as the third confirmed interstellar object. The orbit was archived, the observation logs were public, and the story was recorded. The universe does not owe us familiarity. It does not pause for our understanding. It simply exists, vast and indifferent, offering glimpses of its complexity to those patient enough to watch and humble enough to admit when the glimpses do not fit the patterns we expected. 3 Atlas is gone. The data remains. And somewhere in the cold between stars, an object tumbles through the dark, carrying with it questions we could not answer and mysteries we may never resolve. This is not science fiction. This is January 2026. The story ends not with answers, but perspective. The universe does not owe us familiarity. There is a moment in every investigation when the search ends and the reflection begins. For 3E Atlas, that moment arrived in early January, as the object faded from view and the telescopes turned elsewhere. The data was archived. The papers were submitted. The debates continued in journals and conferences, as they always do. But the question remained. Not, was it artificial? That question was never answered, because the data never demanded it. The anomalies were real, but anomalies alone do not prove intent. Nature is stranger than models predict. Comets are more complex than equations capture. And rarity, however uncomfortable, is not impossibility. The question was simpler. What changed? Before perihelion, the object behaved. During perihelion, it was hidden. After perihelion, it did not. The tail persisted. The rotation changed. The chemistry arrived late. The acceleration continued. And the sun, which should have explained everything, explained only part. Maybe the nucleus was porous. Maybe the layers were complex. Maybe the subsurface reservoirs released gas on timescales we do not yet understand. Maybe the models need refinement. Maybe interstellar comets are simply different. Maybe. Or maybe we watched something pass through our solar system. Something we could measure but not understand. Something we could track but not explain. Something that reminded us that the universe is vast and we are still learning to read its language. The atlas is gone. The data is not. And the next interstellar visitor, when it comes, will be met with better questions, sharper tools, and the humility born from watching something slip away, unanswered. This is not science fiction. This is where the data stop behaving. And this is where we begin again.